next speaker is Gabriel Kerr, speaker of Lagrangian intersection in phase tropical hypersurface.
Thank you. Well, it's a pleasure to be back in Miami in person. I probably won't get to the intersection part of this talk. I just want to describe the Lagrangians in this phase tropical. And this is going to be a sort of elementary talk, very, I think, down to earth, hopefully. But I'll start sort of with some reference to mirror symmetry, since it's a conference on mirror symmetry, and maybe the motivation for why I'm interested in phase tropical hypersurfaces and Lagrangians within them. So start with some motivation from homological mirror symmetry. So we can consider, say, a Laurent polynomial W and look at the fiber and get a complex hypersurface. So this will be some hypersurface inside of a complex torus. And if, as I said, W is a Laurent polynomial, we can consider its Newton polytope, which I'll write as Q for now. And in homological mirror symmetry, there's well, there are several formulations, but I guess pick your favorite, of a mirror for such a situation, for the Fukaya category of this hypersurface. Say you have some, maybe look at the complex torus as the cotangent bundle of the real torus, so you have a symplectic structure. And one of the statements is that this should be quasi-equivalent to matrix factorizations of some toric variety, right, Q tilde, that's not the same Q, with some potential lowercase w. So xq tilde is n+1 dimensional. Sort of you increase the dimension by 2 of the hypersurface. And there's some nice formulations by several authors, maybe Oru, Abizade, and Katsarkov give one of these mirrors. Now, where I come to this story is, as I was originally interested when capital W is a mirror to a toric variety, so mirror potential, to say X sub sigma, a different toric variety. Sorry. And there's a Fukaya-Seidel category of W. This does not, so for the first case, we don't need this to be this W to be such a mirror, but okay, in this case, there's a Fukaya-Seidel of W, and this is conjectured to be quasi-equivalent to the derived category of sheaves on the toric variety, R stack. When you have this situation, there are these restriction functors. Well, maybe on the Fukaya side. I'm sorry? Yes, no, okay, that's a theorem. Well, okay, let's say it's, yeah, okay, we'll say it's a theorem, sure. There were different points at times when it was stated as a theorem, and maybe now we can say it's a theorem. So there's a restriction functor to the Fukaya category of the hypersurface, and there is a stabilization functor in this case. So in this case, xq tilde is going to be just the total space of the canonical bundle of X. I'm sorry. Okay. All right. So what is the motivation then? So one of the motivations that I have is to really try to get a better understanding of this quasi-equivalence up here. In particular, the assignments of certain types of natural objects in here to natural objects in the Fukaya category. And in particular, I'd like to see some certain Lagrangians that would come from this mirror correspondence. But in order to do that, I need to give myself some nice structure for Y. And that's in large part the motivation for this from phase tropical hypersurfaces. Okay, so a goal is to maybe produce, let's give a geometric description of functors. Maybe equivalence. And two, to produce a combinatorial. This is a sort of a lofty goal, but well, it's a work in progress, so we'll see combinatorial versions of these categories. Maybe I'll just stick with Fukaya Y. There are other approaches to accomplish these goals than phase tropical, of course, but okay. All right, so I'm going to jump right in now with that motivation in mind and just talk about in a very elementary idea, but one which I find kind of interesting. So this is just the tangent space, say, of boundary of a cone. Okay, so it'll be very, as I said, down to earth, so hopefully understandable. So I'll take Q a polytope in a vector space NR. I just want Rn. And for now, I'm just going to take A to be the vertices of Q. All right. I'll denote by NQ the normal fan of Q. And this will be supported in MR, the dual of N. And then we can define, of course, this function, which is essentially the tropicalization of Q, maybe, I don't know, some trivial valuation. So this is just the minimum over all the vertices. And this gives us a fan. Well, this is a function. This is a piecewise linear function that's supported on a fan. Finally, I'm going to look at the graph. I'll call it Y sub Q will equal the graph of FQ. And this is just in MR. Sorry. All right. So I'll show some pictures in a moment, some sketches, but a simple example that we'll look at would just be take an interval. Use this guy. Take an interval and take something like this. This is my graph. So I want a tangent space here of this guy. Of course, we all teach in calculus that this is not differentiable, so there's a problem with a tangent space at this corner here. But nevertheless, I still want it. So in short, I'll give the definition of what we can do. So we'll define this to be the union of all supporting tangent planes. or hyperplanes if you want. So more precisely, we can talk about sort of the gradient of our function fq at a particular point x. Here x is in MR. And this is just going to equal the set. So it's not a single cotangent vector. It'll just be the set of cotangent vectors that are supporting. So you can, there's several different ways of seeing what this is, but I'll just define it this way. So fq is less than y as a function. This is in fact a face of the original polytope q, but okay. And then you can define this tangent. Well, this is the precise definition of this tangent space. It's going to be all of these points, oops, where I just basically take a point and take any vector, any tangent vector, and then I evaluate it with respect to any of the gradients. Take the graph of any of the gradients.
What is comparing?
So y is in NR and x is in MR. So it's just the evaluation. So this is here I'm allowed x and x tilde are any two vectors in MR, and y is an element of the gradient. So basically what I'm doing here is, if I'm in a smooth point, I've got my tangent space, we know what it is. But at these corner points, we're taking all of the possible supporting hyperplanes, just taking their entire unit. That's the idea. Okay. So there's a fact, and this is a fact that one of the things I want to talk about. And this is, you can get to this in a lot of different ways, but one way is, I'll show, is that this is in fact the support of a fan in MR R squared. This is so let me give the definition, and then I'll go through some examples. So to define this fan, I need to define a very simple polytope that we can derive from Q, which I'll call the graph polytope. But it's how do we define it? So, well, if I take a vertex of Q, let's let I sub alpha be the interval from, say, 0, these are in MR cross R, to alpha minus 1. And then this graph polytope is just the Minkowski sum of these. It's a zonotope. So all of these ones. Basically, so zonotopes are helpful, of course, if you want to look at their normal fans, because they give you hyperplane arrangements. So these are sort of you're just taking your sort of extreme supporting hyperplanes and letting them divide up your space MR cross R. And so then it's not maybe too surprising that you'll get a formulation of this tangent space as a subfan of this product itself. But let me give the formulation here. So call this the graph. We call it zonotope or polytope of Q. All right, so There's some elementary facts which aren't hard to see, but the faces have a natural interpretation. So they're labeled by partitions of the vertices, A plus, A minus, A naught, which can be realized by essentially just taking an affine function and taking the positive values where the affine function's positive, 0, and negative. So I'll say that. And then this tangent space, maybe it's right, this is another fact, then can be written as this union over all the faces of Q such that sort of the non-negative and non-positive parts of this partition intersect Q non-trivially. And here we'll write down this. So this is a formulation. So now the reason I'm kind of mentioning this is this gives us a way of understanding the local structure of this tangent space at a corner point. And we want to do that so that we can understand maybe an interpretation of what a Lagrangian might look like locally by using this fan structure. I'm going to show some pictures. This is a lot, I know this is notation heavy. I'll get to pictures in just a moment. Let me just write down, okay. Let me say where this lives, and then I'll give some pictures. So this is in this normal fan of these guys. Yeah, so a lot of I sort of started in the opposite direction of picture worth 1,000 words. I started with 1,000 words. Okay. All right, so let me give some pictures here. So the example I started with of taking Q. So here we have an example where Q is just the interval, and the graph is just this sort of absolute value function. This is our graph polytope here, where again you put Q in sort of -1 and then take the Minkowski sum of the intervals from 0 to the vertices. So you just get a square here. The normal fan, you can sort of denote the cones based on sort of, again, where affine functions are positive and negative. And then you can assemble these together to get this total tangent space, or this tangent space of this graph. So over the various strata, for the blue strata, you of course just get the tangent space. Red strata, you get the tangent space. But right at the corner point, you take this fan here, and you can see that there's certain cones in that fan that actually reflect the union of the supporting hyperplanes. So of course, this is a support of a fan, but this fan is not it's not in a linear subspace. And so when you glue these together, you'll get something that looks like this here. And so maybe a theorem, which I'll write real quick, is that if you take any Q, sorry, this should be Q here. This is homeomorphic to R2n, which is something you would like for the tangent space of something that looks locally like Rn. So this is a homeomorphism. And this is sort of a key ingredient in the proof of Viro's conjecture. This is due to myself and Ilya Zharkov. And what the idea here is to take this picture and project. So here we have this tangent space. This lives in MR cross R cross MR cross R. And you want to project this to the second factor of MR, which is essentially your tangent vector, and see what the fiber is. So this is an onto projection. And what you'll see when you look at that is you'll see that, for some reason I can't get the presentation on this side. You'll see that over a single tangent vector, you get something like a staircase, some kind of staircase picture. And this is essentially drawn in this green line here as well. So to illustrate this maybe in a higher dimension, so this is sort of the easiest dimension to work in, of course, when Q is an interval. Once you get more complicated, it gets rapidly more difficult. But here's some pictures that maybe we can look at. So if you took Q to be, say, a square, your graph zonotope becomes, as I said, a bit more complicated. But you have a more complicated corner points occurring as well. Nonetheless, you can take the normal fan of this graph zonotope, and you'll get certain regions. For example, here you can see that you can take away all of the sort of the top maximal cone and the bottom maximal cone. What you're left with is this filled out region, and that's giving you sort of the supporting tangent space of this corner point. Everything left over is. And then when you take one of these fibers from this picture here of some tangent vector, what you'll get is some kind of staircase picture like this. As you move around in this X tilde space, those stairs will sort of adjust, but they're all homeomorphic to Rn. So you get this kind of R2n manifold. Okay. So maybe the main advantage, I'd say, of doing something like this. So what are the pros and cons of answering this naive question?
I have a question.
Yes,
So
please.
In this square subdivided into 4 squares, shouldn't you have
Yes.
Again a square over the origin?
So this square. So I'm starting with my polytope Q.
Where is it? Okay.
That one, yeah, that square. Okay, so this subdivision here is not really a subdivision. It's supposed to be a cartoon, like a sketch of the graph of sort of taking the minimum over all the alphas, all the vertices. So some kind of convex thing. Okay. So now what is the question there?
Well, but now you want to take the tangent space.
Yes.
Where you kind of allow these supporting hyperplanes
Yes.
to wiggle. But wouldn't at the point where these four
Yes.
squares come together,
Yeah.
shouldn't it should be something two-dimensional? Like
No,
it's there because
you're taking the union of all of them. So for one of them, no, it's not two-dimensional. The tangent space at a point is actually, you can get excess dimension. You get like more dimension than you should.
Right.
Right. So if you take, what's wrong?
The tangent space at the point.
At this point, at this red point,
Yep.
is going to,
Two-dimensional.
is, if it were smooth, it would be. But yes, in this case, it's going to be three-dimensional.
Or even three-dimensional.
Because you're taking the union of all of the tangent spaces that support it.
Three-dimensional.
Yeah. So this is the cartoon sketch of that.
But then I don't understand the lower right.
It's not a good cartoon sketch. So basically, you don't understand the lower, which one?
The lower right.
This one.
Yeah.
That's a different projection. So here, yeah, so if I were to project, yeah, so if I project to the point on the graph, going from this picture, then I would get this picture here. The one, I'm sorry, it's having a hard time.
I can't see where you're pointing.
Yeah, I understand that. Let me, here. So if I project to the red point, this is the fiber. Now, however, that is projecting to the first factor. If I project to the second factor, what I'm projecting to is sort of, I'm fixing a tangent direction. And I'm asking as I move, I'm looking for the inverse image of that tangent direction. And the point is over these cones, over this cone, I've got a smooth space, so the tangent direction is just one point. The gradient is only one thing. But then once I hit this kind of edge here, I've got a larger gradient. So I kind of have multiple, inverse images there. And that gives me sort of like, so it assembles into this larger staircase. Is it a little more clear? Or?
I'm still a little bit lost by it, but continue. I mean, so you're saying over the edges you get something one-dimensional, right?
Over all of the other strata.
Zero-dimensional, but shouldn't you then get at the point something two-dimensional? But you still draw it as a line, where it is a line segment. The stair diagram.
In the staircase, so what happens over so if I look at the normal fan of Q, right? The faces, the cones of the normal fan of Q correspond to faces of the original Q, right? So once I hit one of those non-maximal cones, I hit a face that's not a point, right? And so the gradient actually equals that face. And then I evaluate that face on X tilde, and I'll get a line segment. So over every other strata, I get sort of a line segment moving up. And that's what, those are the kind of vertical parts of the stairs. That's what, yeah.
One is, you could make same definition for like any kind of convex function.
That's true.
Would it always be true that the tangent space is homomorphic to RF?
I believe that our proof should work, yes, because this is just only about convexity. Our proof relies on convexity only. But once you get out of convex, it's false.
If you have like a smooth thing which is converging to your graph, with a tangent space as a section.
Yes, there's a Gromov-Hausdorff limit. Yeah, you take the tangent spaces of those smooth things that are converging, and you'll actually hit, this limit. You'll get R space.
You also
that I think is more. I think that's probably Bureau. Like goes maybe even farther back. That's something that's been around. But I don't know if it's been expressed precisely this way. You won't find that proof in our paper, that's for sure. But I think it's not too hard. Okay, so the advantages are that, well, this is as you have strong combinatorial control. So you have good combinatorics. You can identify a bunch of strata. You can build things, as we'll see in a moment, sort of by hand and have good control over where they are. That's, I would say, the main the main advantage. I would like to write advantages, but I think that's probably the best advantage that we have here. The disadvantage, it's maybe more extensive list, is, well, so this guy is not in any sense smooth, not smooth. So, and in fact, putting kind of a smooth structure on it, well, it's possible, but it's not natural. Or at least we don't see a natural way of doing it. And then that, of course, leads us into the fact that this is not really symplectic in any sense. And so if we're going to do Fukaya categories on something like this, well, you have to, these are things that have to be addressed.
Sorry, why was it supposed to be symplectic?
Well, so the idea, so I'm going to get to this in a second. Actually, this sort of next part is to talk about the phase tropical hypersurface. And the idea is that, well, as we'll see, this phase tropical hypersurface is homeomorphic to an actual complex hypersurface. And so we have this, well, for the smooth hypersurface, we have a nice symplectic structure, and we'd like to sort of transport that out. But so it's not supposed to be. The answer, quick answer is it's not supposed to be.
Why is a complex hypersurface supposed to be symplectic?
Well, if it's in something that is symplectic, it should be symplectic. How's that? Or Kähler. The point is the motivation for studying this is to try to talk about a Fukaya category. And what I'm trying to bring out is that this is not smooth and therefore certainly not symplectic. And so talking about Fukaya categories, we need to say more things. That's all.
And why does it bother you? Why not just take this kind of limit, smooth thing?
Well, sort of regenerating things, maybe I lose a little bit of the combinatorial control. Let me just put it. Maybe I shouldn't be bothered. It's a good question. All right. So let me talk about the phase tropical hypersurface, which has been around for a bit. And was sort of defined as one of these limits of smooth hypersurfaces, in the tropical sense. So I'm going to have the same notation as before. But I'll allow now for A to actually not just be vertices, I'll allow A to be a finite set of points. It must contain the vertices of Q, but we'll say this is a marked polytope. And I'm going to add an extra bit of structure, which corresponds to some sort of maybe some valuation in the tropical setting. But for me, it's just going to be a function from my set A to Z. Of course, A, I also should say this, I want this to be a latticed polytope, so I'll assume that A is contained in N. It's fine. So what you get from eta is you get a couple of things. One, you get maybe the first thing you get is you get some tropical function, which is similar to the one I defined before with a trivial sort of valuation. But now we have this extra eta involved to sort of adjust, add some constants to our minima. So this is alpha, say plus eta. Okay. And sort of dually, you also get a subdivision, coherent subdivision of Q, which I'll denote by S sub A. So let's call it S sub A, or S sub beta, pardon me. All right. And these things work together, as is well known, elementary tropical geometry. You get this sort of bijective correspondence between, say, if I take a cell in the subdivision, I can talk about its dual cell in the stratification, sort of the, maybe I'll call it the strata of this trop. So lowercase trop is a function. The the corner locus, of course, is our tropical hypersurface. But we can also include, the maximal strata as well, if you want, in this bijection. Okay. So maybe an example here that I drawn is given here. So I'm assigning here. I just have A as the points. I'm putting a -1 sort of brings down one of the one vertex, and then taking sort of the subdivision induced by that gives us a triangulation in this case. Yeah, so this is the usual story here for inducing subdivisions. I'm going to assume actually that I've chosen this eta rather generically. So I'm going to want this to be a triangulation in order to talk about this phase tropical picture. Okay. So now, in order to define this, there's several ways of defining this phase tropical hypersurface. I'm going to give a sort of by hand definition, prescriptive definition, little recipe. We need a few ingredients here. And then we'll assemble them. To get our full guy. So we're going to need a subgroup of MR, which I'll label M sub sigma. So first, let's choose any simplex in our triangulation. We'll need a subgroup. This is going to contain M, might be equal, and it's contained in MR. And what is it equal to? Pardon me. This is just the set of points in MR that evaluate that when I essentially look at them on the difference of vertices of my simplex, that I'm an integer. Alpha and alpha prime are in sigma. So this is one thing I need. I'm going to define some open polyhedra. And what are these going to be? These are going to be defined by essentially the same kind of pairing, but now we're just going to assume that the absolute value of these is less than 1/2. Here again, alpha and alpha prime are in my sigma. And from these two things, we can define essentially a co-amoeba, what we call co-amoeba cover. And we just take our polyhedra and we translate it by our subgroup, and we subtract what we get from all of MR. Let's see. So this has an action by M, and to get the co-amoeba, we just quotient by that action. This is for any given sigma in our triangulation. Okay, so these are the ingredients we need. And then using these ingredients, we can assemble them to define a phase tropical hypersurface. Do that now. So phase tropical hypersurface induced by eta is given by just this, I'll denote it script T sub eta. And it's just the union over all of our simplices. And you can sort of disregard the vertices because the polyhedral are going to be empty for those cases, but we don't need to do it unless we want to. We take the dual strata in the tropical variety of sigma, and we cross that with our coamoeba. And we get this guy. Yep, I'm gonna get to a picture.
But also, in what set? This is a subset of what?
Okay, good. So this is a subset of MR cross MR. So I should warn people, like the MR used in this tangent space part is going to be sort of not the same as this MR. This MR would be like one. This is one more dimension. This is like the MR cross R. So this is where this is. So in a sense, maybe Benjamin's question, like, so there is no reason at all to feel like this is symplectic. This is very much complex, right? So this is MR cross MR, something crosses tangent, has maybe a natural complex type of a structure. If it were MR cross NR, maybe we would feel better about a symplectic structure. So there's not a real reason to believe there is a natural structure.
I want to divide off by M on the right hand side, MR cross MR on it.
Yes, thank you. Thank you. I'm doing the, yes. I often don't mentally do that, so, but yes, you're right. So if we had sort of the dual, so this is a, maybe one way of thinking about this is, or maybe not a correct way, is some polyhedral limit of your integrable system. So if we were to take the dual system, we get something more symplectic looking. This is more the complex story. All right, to the pictures. So I looked at this particular example. So we have this subdivision, and the tropical hypersurface is illustrated down below, down here. And then over the varying strata, we have different looking coamoeba. These are what I'm illustrating here are the coamoeba covers, and the black points will represent M. So you quotient out by that lattice to get your torus. So at a nice point like sorry, pardon me, at a nice point like here, where you have a sort of a smooth tropical point, you have a unimod. This comes from the fact that we, in the original subdivision, this is a unimodular triangle, simplex. You just have this sort of usual picture of a coamoeba that you would have. When you don't have unimodular simplices, you get sort of the same picture, but now there's more topology going on. So you're quotienting by something less.
They sit in MR, or the thing which after you multiply it by R becomes MR?
Yeah, so let's forget about multiplying by R. So this is, I'm going to kind of come back to this tangent space picture in a second. But right now, this is just an MR,
okay, so
a new MR, new regime, MR.
But is it the same as the one in that definition, or is it?
Yes, it's the one in this part. It's the same in the definition here. Yes, there's no MR cross R yet. Yeah, so everything here, the only place where this is NR, this lives in NR, but everything up here is MR. Everything is in the dual, including the tropical. Now over the strata in between here, your open polyhedra are just these sort of, long strips, so they're actual polyhedra, not polytopes. And taking their complement, you're going to be left over with some linear spaces, some affines, some lines. So when you quotient out by this, you'll get just a bunch of circles. Well, or a circle in this case.
Sorry, Gabe, this is Denis. I have a question about the picture. So over the nice vertex, as you call
Yes.
it, what topology do you have? Because it looks to me like this is a punctured torus, while I was just expecting a pair of pants.
No, you have a torus. It's a usual torus. So we have the MR cross M is just so you're saying over this point, what you have is this this picture modded out by the lattice. So if we were to assemble maybe locally, maybe I'll draw this picture and this will help. Locally, you get this picture here. I mean, which I think people have seen multiple times. So you get this picture here. Over these legs, you get circles. And then when they come together, you're going to get these two triangles, and they're reflected in, there's a bottom side of that triangle. Is that, people see that? Denise, is this answering your question?
Yes. Okay, sorry, I had the wrong lattice in mind. For some reason, my mind was blanking on 2/3 of your black dots.
Yeah, sorry. So if I quotient out up here, this is what you'll get is this picture here. You'll get two of those triangles will stay, will be in a single fundamental domain, and they'll wrap around each other like that. So some topologically,
Thanks. Sorry about that.
Sorry.
So tropical pair of pants.
Is a what? Is a bikini? Yeah, I think Nick Sheridan called the skeleton of this a thong or something. Yeah, so this is the bikini is a nice. Ours is more like a bikini. We don't actually do the thong, so we have some coverage. Let's put it that way. Okay, so all right. So now, what I want to do is relate what I'm talking about here to what I started with, and just point out that if we zoom in on this picture here, what we'll get is, we'll get this picture, and then we can see that there's going to be sort of 3 points of interest up to this action by M. And now those points don't really glue to all 3 of these legs. Each point only glues to 2 of them. And what you'll see is these 3 pictures. And then from these 3 pictures, what this is supposed to evoke is that each of these pictures, when you assemble them together, these are each naturally essentially tangent spaces of these graphs that we were talking about before. So the local structure of this polyhedral complex looks like this tangent space of one of these graphs. So we get that this is a topological manifold, and moreover, this topological manifold, this is the kind of main theorem of myself and Ilya, said this topological manifold is homeomorphic to a hypersurface Y, which is W inverse is just a hypersurface given by a generic Laurent polynomial whose Newton polytope is Q. So generic coefficients. So the big stumbling block was showing that this was, one of the big stumbling blocks was showing this was a manifold topologically, but then after that, you can use Mikulkin's Parapansi composition and some nice cellular decomposition of both sides to prove that they are homeomorphic. Okay. So now, the last 10 minutes, what I want to do is talk about what if we were to put a symplectic structure in some combinatorial sense on this phase tropical variety, what kind of objects we might find that would be sort of nice Lagrangians. So maybe before I get to that, let me just show the higher dimensional picture. Of course, doing all of this in one dimension, one complex dimension, is not too hard. The real difficult part of this theorem and the earlier work is to really consider higher dimensional spaces where you can't get such simple drawings. But nonetheless, these higher dimensional cases people may have seen before. There's several people who've considered this, where you have a pair of pants, say a two-dimensional pair of pants. Here, your open polyhedra is this zonotope, at least for the vertex. And you'll get some kind of tessellation looking. I mean, it's not quite a tessellation, but you'll get some coamoeba cover, which I'm partially drawing here. And again, what you'll get if you look at these vertices, remember that the coamoeba is the complement of all of these polytopes. And so what you'll get is you'll get this local structure, which looks like the other example that I was showing in the beginning, sort of the complement of these two cones. Okay. All right, so now two Lagrangians. So I think I have maybe enough time to talk about thimbles. So I'll talk about thimbles. So the way I define these open polyhedra was that they're polyhedra essentially through the hyperplane representations, some bounds on given by the dual vectors. But the more common way, especially of describing this zonotope that you see pictured here, is to really describe it as a zonotope. And that works well when you're dealing with a vertex. So I'm going to talk for a moment about that other way of talking about these polyhedra. So alternative formulation of P sigma for full dimensional sigma. Move this over a little. Well, so here we have some single simplex sigma, and we'll have, let's say it's n-dimensional. We'll have n vertices, and of course we have the opposing faces, facets, which we can label. And then from this, we can look at the tropical fan associated to it locally. And because everything was defined integrally, we can take our primitive vectors here, which are dual. So we'll have W1, W2, and W3, sorry, W naught. And if we do it this way, one can show very easily that the open polyhedra is just the Minkowski sum, I equaling 0 to n, of these of 1/2 of these intervals, 0 to wi. So we just take the open interval from 0 to wi, take this Minkowski sum, we get this. So this is, I think, more commonly the way people, at least in the literature, write these polyhedra, these zonotopes. All right, so now what I want to do is I want to use this formulation to define a certain class of other polyhedra, very simple. I think this is one of the reasons I'm drawn to this, is this is a very simple kind of definition. So let's give it. So let's focus on a face sigma, and define the tube tube. So we think about cubes and tubes, b sub tau. So this is going to be the dual strata corresponding to tau, and then we're going to cross this with the sum, Minkowski sum of not all, but now just those alpha I, those I for which alpha I is a vertex of tau. And we'll take the closed. So this is going to be this really will look like one of two things. So case one is that tau is full dimensional, then its dual is just going to be a point. And so this is just going to be this zonotope. This is going to be the closure of the polyhedron, open polyhedron. And then the other one is that this is going to be, so otherwise, this is a tube, cubical tube. It's a tube. So maybe cone cross cube. I mean, I say cube combinatorial. It's be square, cube, whatever. All right. So now, this is some nice polyhedron, but now what we can do is we can take this polyhedron and we can intersect it. This lives in the same space. Note that this lives inside of MR cross MR. And most of it is disjoint from the tropical phase tropical hypersurface. However, we can look at the intersection of, and here I'm going to take the cover. So I'll write this as the cover so that I can be in MR cross MR. Data, pardon me. I should say, so here everything I'm considering, since I'm doing thimbles right now, what I'm going to do is I'm just going to take Q to be sigma, Q just to be a simplex, so that I don't think I'll have time to do the more general setting. So here Q is just the full simplex sigma. And so what is L tau? It's this intersection. And then I don't know if I want to say, so let me call it a proposition. It's that in case one, L tau is a topological sphere. In case two, tau is a ball. And the idea is that this should represent the thimbles that you will see in symplectic geometry when you're, okay, if you were to tropicalize a Landau-Ginzburg model locally. So I think I have just enough time to show some pictures of what this looks like, and then I'll finish. So the first couple of cases is it's very simple. So if we take sigma to be the entire thing, well then, as I said, if you take this b sub sigma, it's just going to equal this the zonotope itself, this polyhedron, this p sub sigma, the closure of it. Once you put that in, of course, that inside of the phase tropical variety, most of it doesn't intersect. We've taken out the open interior, and so what we're left with is just the boundary, which will just be this hexagon. This is, once you quotient by the M action, this is actually what gives you this Sheridan sphere and the mirror symmetry of the pair of bands, once you smooth it. However, you don't have to take the full sigma. You can take, sorry, this should be tau here. Sorry. You can take a face of sigma, say tau, And now when you take the Minkowski sum, you're just taking two of them, so you just get some parallelogram. You cross it with this cone here, and you'll get sort of a ray cross parallelogram, so some rectangular thimble. When you intersect it with the phase tropical, you're going to get sort of 2 points over the fiber here, and then you'll just get this sort of lower boundary when you look at this on the coamoeba over the vertex. So you'll get this sort of thimble traveling out. And then finally, I tried to give one three-dimensional picture. So if you take this tau here, this all should be tau, is just a face. So that's the two-dimensional face facet of this three-simplex. When you take this Minkowski sum, you'll get a cube. You're going to cross it with a ray. And then when you intersect this with the whole thing, what you'll get is you'll sort of get parts of the cube will survive on the intersection over the vertex. Then the rest will sort of travel out as a boundary of the thimble going out. So what we can do, which I didn't have time to get to, is we can sort of glue these together and build actual spheres. And we can use some of the additive structure of this ambient MR cross MR, sort of do some natural twists as well. So we can build a lot of different spheres and thimbles, sort of by hand, control their combinatorics, and look at their intersections. What we can't do is problems that we had with the symplectic geometry and the smooth structure. We want a version of Lagrangian Grassmannian in this case, so that we can grade these and get these intersections to really well, have a grading. And we would like to have, ideally, an interpretation of the infinity maps and a combinatorial setting as well. But we are a little bit a ways from that. But this is where I'll conclude the talk. So thank you.
So did I understand correctly? So essentially what you're doing is you're looking at these piecewise linear pictures that you get as tropicalizations. You view it as a phase tropical object, and then inside the phase tropical object, you identify things that look like a fibrations, off-dimensional subcomplexes.
Yes. So I think that's a good summary. So we're looking at the phase tropical. So we have the tropical version is, of course, is half-dimensional. So the phase tropical gives us the full topology of the hypersurface. You can tropicalize, as I said, the Landau-Ginzburg potential as well. So if you restrict certain functions to sort of a given given hypersurface, you can see sort of a function as in a tropical setting, and there, well, our thimbles then actually turn into actual thimbles of the potential, or should be tropicalized versions of those things. So this gives us some notion of what the vanishing cycles coming from a Landau-Ginzburg potential might look like in the fiber. So what this restriction functor was in the beginning. Yeah.
Is there do you know the sense in which hypersurface converges to the phase tropical hypersurface?
Yeah. Well, okay. So there's this Gromov-Hausdorff limit in that sense. I don't know if
that true? There's some
yeah.
Some way of doing some descaling.
Yes, there is. Yeah, and this is I think this. I don't know if I should say Bureau is maybe the person to refer to this originally as, but I think in yeah, I'd have to look a little bit to see the precise reference, but yeah, this is known.
You showed that the hypersurface is actually homeomorphic, and together with the work showing that it's actually embedded
Yeah, they're looking, well, so there's a limit, there's a topological limit, which is one thing. To say that you can maintain the smooth, the smooth structure or just even the topological structure is a different statement. So you can say this converges in some kind of weak sense, but yeah. Yes, exactly. That's what I'm saying. So that's what our paper was about, is really that we could recover the topology in this limit.
But it is also true that.
Yes, it is true. Yes.
Tropical geometry sometimes shadow is not a key. Is there some similar?
I didn't hear you. Shadow what?
So tropical geometry, certain people is the image of non-Archimedean geometry and evaluation. Is there some similar explanation of what is tropical geometry?
Okay, so yeah, that's a very interesting question to me, like as far as how to interpret a lot of these things. We have a lot of different models that we've looked at for sort of the phase portion. One of my favorites is that you can take sort of the AN root system and you can take the sort of alcove decomposition of the full thing. And then all of these polyhedra and so on are sort of unions of alcoves. So there's some sort of representation theoretic thing going on with this. But I don't have a good fix on it. So I can't really answer the question. I can just say there's certain things that look like they have to do with, other mathematics, discrete mathematics, and something. But I don't know where the valuation portion comes in with the phase. There is some representation theory thing going on. I think.
So let's